So we are going to solve this question related to acid-base equilibria. In this question, they've asked us to calculate the pH of a 0.0025 molar piperidine solution. What is piperidine? Piperidine is a colorless liquid having odor of pepper. Its pKb value is given. So it's acting as a base. It's a nitrogenous base, C5H11N. So we are supposed to calculate the pH of this solution of piperidine. Let's explore this. Let's plan out how we are going to reach our target. So C5H11N, which is piperidine, it's a nitrogenous base. In the aqueous solution, it takes the proton from water, takes the proton from water and yields C5, that is protonated piperidine plus hydroxide ion. So if we could calculate the concentration of hydroxide ion, which is here, if we could calculate the concentration of hydroxide ion, we'll be able to calculate the concentration of H positive ion, and from there we can calculate the pH of the solution. So let's apply the ICE methodology, which is initial, change and equilibrium methodology. Initial concentration of piperidine is given to be 0.0025 molar. When we started, we didn't have any product, so the concentration is 0. The concentration of hydroxide ions is nearly 0 because some of them, they're coming from the auto-ionization of water and we are ignoring them at this stage. The concentration of the solvent we are not going to take because it's present in a large amount, so we are not worried about what other concentration changes happen in the solvent, so we'll leave that. As the reaction proceeds, reactants are being consumed, so their concentration is bound to decrease. Products are being formed, so the concentration is increasing as the reaction proceeds. Suppose X moles per liter of piperidine, they get consumed as the reaction proceeds, so this much is the change. So the same amount of products would be formed. X moles per liter of protonated piperidine, X moles per liter of hydroxide ion. Because if you look at the equation, 1 mole of piperidine yields 1 mole of protonated piperidine and 1 mole of hydroxide ions. So at equilibrium, what can we expect? That the concentration of piperidine is what we started with and how much is consumed. If we subtract this, we will get how much would be the amount which is left at equilibrium. So this comes out to be this. And of course, this would be X moles per liter, X moles per liter. These would be the concentrations of the products. So if we could calculate X, which is nothing but the concentration of hydroxide ions, we would be able to calculate the concentration of H positive ion. Given that the concentration of H positive ion and hydroxide ions, that is constant, like in water, if you see that the concentration of H positive ion and concentration of OH negative ion, the product of those concentrations is always 10 raised to the power minus 14. So we could calculate that. Or we also know that pH plus POH is equals to 14. So either way we could do this. Now, using all this, please keep this value. I'm going to erase this off. Keep this value in your mind. That is pKb is equals to 2.89 for piperidine. So if we focus on this equation, we can write down the Kb, that is the dissociation constant of this base, as concentration of products C5H11N H positive. Okay, so we'll write down the concentration of this multiplied by the concentration of hydroxide ions divided by the concentration of the reactants, which is nothing but piperidine itself. Okay. So this is, we know from our knowledge of chemical equilibrium that the equilibrium constant is equals to the product of concentration of the products divided by the concentration of the reactants, and they're raised to the power by their stoichiometric coefficients. In this equation, the stoichiometric coefficients for each one of them is just 1, so we need not to worry about that. So we'll just substitute these values in this equation. Okay, so what would it give us? The concentration of this is X. X multiplied by X divided by 0.0025 minus X. So this is what we got from there. Mind it, X is the concentration of protonated piperidine, as well as X is also the concentration of hydroxide ions. So we'll proceed. We know that pKb is given to us and its value is 2.89. The value of pKb is given to be. So I'll do it here on this side. So the value of pKb is given to be 2.89. Okay. So we will use this value to calculate Kb. We know that pKb is nothing but minus log of Kb. Okay. So pKb is 2.89 is equals to minus log of Kb. Or we can write it like log of Kb is equals to minus 2.89. Kb is equals to 10 raised to the power minus 2.89. It's just the anti-log. So this was log to the base 10. It was log to the base 10. So when we take the anti-log, it would be like the base, this base, raised to the power by this number. So if you use the calculator or the log tables or any way you want to calculate, so Kb would come out to equals to 1.288 10 raised to times 10 raised to the power minus 3. So we can round this off to 1.3 times 10 raised to the power minus 3. So we get the value of Kb from the value of pKb. Okay, and we will use this value now here. So we will substitute the value 1.3 times 10 raised to the power minus 3 is equals to x square divided by 0.0025 minus x. Fine. So now we will see if we can apply an approximation that x is very small. We can apply this approximation. To check if we can apply that approximation, what we can do is the initial concentration of the base divided by Kb. If it comes out to be equal to or more than 400, then we can neglect or ignore X in comparison to this value. And if it is less than 400, then we have to use the other way of solving this equation and finding the value of X. So the value of B naught, that is the initial concentration of base, is 25 10 raised to the power minus 4 divided by Kb, which is 1.3 times 10 raised to the power minus 3. So if we'll calculate that, okay, so it would be roughly like 13 times 2 is 26. Roughly we can say that it is 2. Yeah, it is. So we cannot apply the approximation here. So this is less than, this is like, if I write it properly, it's 25 times 10 raised to the minus 4 divided by 13 times 10 raised to the power minus 4. Okay, so it's like they will cancel out and it's roughly equals to 2. So we cannot use the approximation. We have to solve it by other ways. So what we are doing is 1.3 times 10 raised to the power minus 3 multiplied by, so I'm just cross multiplying it, minus x is equals to x square. Okay, so if I open this up, it comes out to be equals to 3.25 times 10 raised to the power minus 6 minus 1.3 times 10 raised to the power minus 3x So this whole is equals to x square. If we solve this quadratic equation, you know how to solve it. We use this formula which you have studied in school. Minus b plus minus root of b square minus 4ac upon 2a. Okay. If we solve this using this formula for solving the quadratic equation, we'll get the value of x, and we will choose the positive value here because negative value doesn't make sense, like in terms of concentration doesn't make sense. So if I say the value of b here is, if I just rearrange this equation, I'm rearranging it, x square, so this is x square, I would take this to the other side, so it would be plus 1.3 times 10 raised to the power minus 3 x, okay? So, or you can write it like 0.0013x, okay? Minus 3.25 times 10 raised to the power minus 6 is equals to 0, okay? So this is the equation. So for b, what you will substitute? You will substitute this value. For a, since the coefficient of this x square is only 1, so it is 1. For c, you will also take into account this negative sign of c here so that this value becomes positive. So ultimately, by solving all this, by substituting this value, this is just a simple mathematics. So what you will get the value of x to be 1.3 times again 10 raised to the power minus 3. So this is the value of x you will get. Now, if you could recall, the value of x gives us the concentration of hydroxide ions. So what we can say that the concentration of hydroxide ions for this solution is, so x is equals to concentration of hydroxide ion, which comes out to be equals to 1.3 times minus 3 molar. So this is the concentration which is coming out there. So if you can find out the pOH or the pH, whichever way you want to go, you can go either finding out the concentration of H positive ion, then finding the pH, or you can find the pOH, which is nothing but negative log of concentration of hydroxide ions. Okay, so this comes out to be equals to minus log of 1.3 times 10 raised to the power minus 3, which comes out to be equals to log of 1.3, then this power would come here, so minus 3 minus, so it would come out to be 3 log 10, okay? So you can recall that log mn is equals to log m plus log n, okay? Log m plus log n. Also, if there is like log x to raised to the power n, this would be n log x. So this is what the power will come in the front, and then you have the log and such. So this is what we have done here. So minus log of 1.3, you can calculate this by using the log tables or with the help of calculator. It comes out to be equals to 0.1139. So this is in minus. Okay. Plus 3 log 10. Log 10 is 1 only. So it is 3. So the value of pOH would come out to be 2.886. Okay, so I already calculated this, so I know that. You can use the calculator to calculate this. Okay, so we can round this off to 2.89. Now, we know that pH plus pOH of an aqueous solution, it comes out to be equals to 14. We know pOH, so we can calculate pH is equals to 14 minus pOH, which is nothing but 2.89. So the value would come out to be equals to 11.11. This is the pH of the piperidine solution whose initial concentration is 0.0025 molar. So what strategy we adopted? We tried to find out what is the concentration of the hydroxide ion at equilibrium using the ice table or the ice methodology or initial change equilibrium method, and from that we calculated the concentration of hydroxide ion. We got the concentration of hydroxide ion. Since the value of pKb is given, from there we calculated Kb, and then applying the equilibrium laws, we calculated the concentration of hydroxide ion, of POH, and then pH eventually. I hope this clears this numerical problem. Thank you.